All right, so everybody should have their notes packet out. I need you to turn to the third to last page. We are on lesson 10.6, circles and arcs. So we're going to start out with some basic definitions here. Go ahead and follow along and fill in the blanks as I write. So first off, we have in a plane, a circle is the set of all points equidistant from a given point, which we call the center. We always name circles by their centers. And the way that you can show me that it's a circle is you draw a circle, but you put a little dot in it so that I know it's a circle and not the letter O or a 0. And then you name it by whatever point that center is. So a lot of times we'll call circles circle P or circle Q. And that's how you note that something is a circle, so that we don't need to write out the word circle every single time. A diameter is something we've already talked about. This is a segment that contains the center of a circle and has both endpoints on the circle. A radius is a segment that has one endpoint at the center and the other endpoint on the circle. And if you remember, the radius is half the length of the diameter. So if we have what are called congruent circles, just like we have congruent triangles, that means that they have congruent radii, which is just the plural form of radius. And last but not least, a central angle, we're going to be talking about central angles quite a bit, is an angle whose vertex is at the center of the circle. So make sure you have all of these blanks filled in before we move on to the diagram down below. So in this circle, which we would call circle P, if you want to make a note of that, P is the center. Let's go ahead and label that up here in the upper left. P is the center of the circle. AB, or you could call this segment BA, with a little segment notation above it, is the diameter. PC is the radius, and then over here, angle APC, we would consider a central angle. You could also call angle BPC a central angle as well, as long as the vertex, which is going to be that middle letter, is at the center of the circle. And then we've got a quick note here that we can find the length of part of a circle's circumference by relating it to an angle in the circle. And we're going to be doing that a little bit later on. So we've already talked about finding circumference of a circle. Remember, circumference is 2 pi r, 2 times pi times the radius, or we can use the formula pi d, which means pi times diameter. So we're going to be talking about how if I look at just a portion of the circumference, how I can use that central angle to go ahead and find that fraction of the outer length. All right, a few more definitions here before we get into some examples. Starting with an arc, that's just ARC, is a part of a circle. So one type of arc, a semicircle, which I'm sure you've all heard of, is half of a circle. That means that one of its sides is made up by the diameter. Then we have what's called a minor arc. That is anything smaller than a semicircle, less than a semicircle. And we also have a major arc, which will be larger than a semicircle. So we're going to name minor arcs by their endpoints, and we're going to do some practice with this. And we name major arcs and semicircles using endpoints, but also a third point. You have to have that third point in there so that we know that it is more than just a minor arc. So to give you an example here, if I wanted to name, let me get the highlighter here, this major arc starting at S and coming all the way around, we are going to call that arc STR. And the way that we show it's an arc, we draw an arc right above it. So not a segment, straight line, but it needs to be a curved arc. Then we've got this minor arc here in red, and we would call this arc RS, again with the arc symbol above it, or you could call it SR. The order does not matter. So make sure you have both of those examples written in for me. And then go ahead and flip your notes to the next page, and we're going to practice this. So example 1A, this is asking us to name the minor arcs of circle O. So go ahead and take a couple minutes, a couple seconds here, and see if you can come up with one or two on your own. And maybe even go ahead and try letter B, which is to name the semicircles of circle O. So one of the minor arcs that we should be looking at is going to be right here, AD. So that should be one that hopefully we all got. I also have this matching minor arc on the other side, CE. And then we're going to have the minor arc that goes along the top here that I'm drawing in with my pen, AC, and then below, DE. And again, you might not necessarily have your letters in the same order, but that's okay. So arc AC and also arc DE. Looking at the semicircles, we want to identify the diameter. So DC is a diameter, which means that one of my semicircles is going to be DAC. So starting at the endpoint D, using endpoint C, but also including, there's our third point at A, and that's going to give me this whole semicircle. We also have EDA using AE as our diameter, E to D to A. I could also start here at C, so this is the other half of semicircle DAC. I have C, E, D. And then starting at A, I have A, C, E. So it's kind of that upper right semicircle. And then Last but not least, we're going to take a look. I'm going to erase this part. Let's take a look at some of the major arcs. So this has to be something that is more than 180 degrees, which is the measure of our semicircle. So one major arc, if I start at A and I follow C, I actually have to go past E, that would be my semicircle, and I'm going to land at D. So I'm going to call that major arc A, C, D. You could also call that arc A, E, D, A, E, D, but the one thing you have to have are those two endpoints at A and D. So I also could start at point C and wrap all the way around to A. So I should have arc C, E, A. I could also have E, D, and all the way around to C. So if you notice, I'm kind of changing what my starting point is. And last but not least, if we start at D, jump over A, and come all the way to E, D, A, E, that is my last major arc on circle O. So make sure on your homework tonight, every single one of these, you should have these arc marks written above so that I know it's not a segment you're talking about or an angle, but an arc. All right, a couple more definitions here. The measure of a minor arc equals the measure of the central angle. So in this example, because this central angle is 50 degrees, I could actually say that arc RT equals 50 degrees. To find the measure of a major arc, we're going to take 360 degrees, and we're just going to subtract the measure of the minor arc. So in this example, if I was finding arc R, Q, T, I would do 360 minus 50, and I would end up with, if we do 360 minus 50 degrees, 310 degrees for this major arc that wraps all the way around. The measure of a semicircle, we already know, 180 degrees. If a whole circle is 360 degrees, then half of a circle, a semicircle, will be 180. Next up, we have adjacent arcs. Adjacent arcs are on the same circle and have one point in common. So if I was looking at arc RT, and let's say I drew in another arc here, and I'll call that point M, arc MR, those are adjacent arcs because they share point R. And the last bit to this, for us to define adjacent arcs, is that we can add two adjacent arcs to get the measure of a bigger arc. So if I know that arc RT is 50 degrees, and I told you that this new angle was 30, I would know that arc MT would be 80. So let's go ahead and practice that on the next example. So my suggestion for these problems, put your homework paper over the problem in the textbook and trace the circles. And I like to just start filling in as much information as possible. We know that this central angle here is 32 degrees. So I know arc BC has to be 32 degrees. There's this one-to-one relationship. that minor arc is equal to the measure of the central angle. Over here, letter B, arc BD, that's starting here and ending all the way over here at D. We would consider those two arcs adjacent, so what I need to do is take the 32 degrees that make up arc BC and add 58 degrees for arc CD, and altogether I'm going to get 90 degrees. That should be my final answer. Letter C is asking for arc A, B, C, and I think we can see here that CA is a diameter, so that means that this arc has to equal 180 degrees. And last but not least, letter D is asking us to find arc AB, which means if I know I have 180 degrees for ABC, all I need to do is subtract out 32 degrees, and that's going to leave me with this arc I just drew in with a squiggly line, which puts us at 148 degrees. All right, last up, we're going to now relate circumference to what we call arc length. So the circumference of a circle is the distance around the circle, while arc length is a fraction of circumference. So we know that circumference equals pi times diameter, or 2 pi r, and that just depends on what information you're given. So then the length of an arc, we'll say AB in this case, what we do is we take the measure of the arc, so the measure of arc AB, over 360 degrees. I'm trying to figure out this little sliver here. How much out of 360 degrees is that little sliver? And then I'm going to multiply it by circumference. So I want you to get in the habit of saying that arc length is a fraction of circumference. If you can remember that arc length is a fraction of the circumference, here's the fraction part. Whatever the arc measure is, divided by 360, of tells us to multiply, and then you plug in your formula for circumference. And then we've got one last note here that will help you on some of your homework problems. If two circles have the same center but different radii, they are what we call concentric circles. And we'll see our next example will actually involve concentric circles. So if you know the big radius and the small radius, you can find areas, you can find circumference. You're looking at the difference between those. So let's just do a double check and make sure you have everything labeled, and then we'll move on to our last two examples and call it a day. So for example 3, we have a 2-foot wide circular track for a camera dolly that's being set up for a movie scene. So I know, you can see here, that that width is 2 feet. The two rails of the track form concentric circles. So that means that this center is the center for both circles. The radius of the inner circle is 8 feet, and I want to know how much further does a wheel that's on this outside track have to travel as compared to a wheel on the inside track. So in order to do this, we need two different circumferences. So I'm going to start with the circumference of the inner circle. And I'm just going to abbreviate circle with our little circle symbol. So remember that formula, I'm going to use 2 pi r because I'm given the radius and not the diameter. And the radius for the inner circle is this 8 feet. So I'm going to plug in 2 pi times 8, and to get our exact answer, we're just multiplying the 2 and the 8, and we end up with 16 pi feet. Then we're going to do the same thing, but for the outer circle. So real quick, go ahead and write down what the radius of the outer circle is. I need to take the 8-foot radius from the inner circle and add in 2 additional feet. So we should have gotten a 10-foot radius. I'm still using the same formula, 2 pi r, but now the r value is going to be 10. So that means that the circumference of the outer circle is 20 pi feet. And in order for me to answer the question, how much further does a wheel on the outer rail travel, I want the difference between these two. So I'm going to take my bigger circumference, 20 pi, and subtract my smaller circumference, 16 pi, and I get a difference of 4 pi feet. That would be my exact answer. And if I asked for an approximate answer, you would actually, in your calculator, type 4, and then using the pi button, times pi. That works out to be about 13 feet. Typically on a test or quiz, I am going to ask for the exact answer, meaning that I want you to leave it in terms of pi. So let's go ahead and take a look at our very last example, and then you guys should have some time to get started on your homework. So here's where we're going to practice finding arc length. So in example A, it's asking for the length of XY, which is this red outer piece to the right. So the first thing we need to do is figure out the measure of that arc. And since I have a little right angle box here, I know that the arc's measure is 90 degrees. So when I think that this arc length is a fraction of, remember of tells us to multiply, circumference, my fraction comes from taking this arc measure, 90, over 360, and multiplying that by the circumference. So I'm going to use pi d as my circumference. Because I'm given a 16-inch diameter, I want to use the circumference formula that is pi times diameter. So the first thing I'm going to do here is I'm going to cancel out these zeros. 9 over 36 reduces down to 1/4. And I think we can all see here that this arc that we're trying to find is split into 1/4 of the circle. That's the fraction part. And then the whole circumference is 16 pi. So if I asked for the distance all the way around this circle, my answer would be 16 pi. But in this case, I'm looking at 1/4 of that, and we know that 4 divides into 16 4 times. So my final answer is 4 pi inches. So we're going to do that same thing on this next example, except you can see here we are given the radius. So now the circumference formula that I want to use is 2 pi r, since that's the piece that I have. I am trying to find x, p, y, which hopefully we can all see is the major arc of this circle. So the fraction part that we wrote out over here, that comes from 240 degrees out of 360 degrees total. And then I'm just going to plug in my 15 centimeter radius into my circumference formula for r. So times 2 pi times 15. And right now we're just going to treat that pi as a variable, so we don't need to touch it. Here again, I can see that the zeros cancel out. 24 and 36 are both divisible by 12. So if I divide 24 by 12, I get 2. And if I divide 36 by 12, I get 3. And then here, my circumference, 2 times 15, gives me a 30 pi. You can put this over 1 if it helps you. You could multiply straight across, 2 times 30, and then divide by 3. I like to cross cancel. 3 goes into 30 10 times. And now I'm just left with 2 times 10 pi, meaning my final answer will be 20 pi centimeters. So that's it for today's lesson. We've got homework listed at the bottom of the page, and I am just double checking and making sure this is everything that's listed on your homework calendar, so you can use the last 23 minutes or so of class to be working on this homework assignment. Remember that I am going to be collecting your 10.6 along with 10.4 and 10.5 all tomorrow. So make sure you have all 3 of those assignments done. We're going to put together kind of a little mini math packet. And hopefully everybody's being great for the sub. Good work today.